Hello, good morning, good afternoon, good evening, everybody, wherever it might be. It is my great pleasure to welcome a co-organizer of the seminar, Wojciech Szymański from Odense. This is, I think, our second Danish talk. We already had the Richard Nest. So, and we still expect two more talks from Odense. So we have this Danish domination of the seminar, and Wojciech is a prime example of it. And he will tell us everything and more about the conjugacy of Masas in graph sister algebras. Wojciech, the floor is yours, internet is yours, Zoom is yours, take it away.
Thank you very much. It is always a great pleasure to be in the seminar. So I should, of course, start by thanking the organizers for giving me the opportunity to speak here. So many thanks. Well, actually, I think it's my second talk at this seminar already.
Yes, it is. Yes.
Maybe the previous one was roughly a year and a half ago. So since everyone remembers every word I said, I can straight away continue. No, this will not be a continuation. It will be actually a completely different subject, a different work with different collaborators. So maybe let me briefly mention. Okay, as always, you know, work is based talk is based on many things, but the most recent paper that I would like to advertise here, which is on the archive, was written in collaboration with Tomohiro Hayashi from Nagoya University of Technology and Jong-Hee Hong, who, currently actually is my a co-worker at my friend from University of Southern Denmark in Odense. So yet another Danish connection here in this seminar.
Yes.
These Danes are really multiplying and dominate these events in operator algebras, which is good. Okay, so let me get started with some mathematics. Okay. All right. So let's so what we are talking about, conjugacy or classification of Masas, that is maximal abelian subalgebras of some algebras. Later on we'll be just specifying about graph algebras. So suppose that A, B are two Masas of a unital star algebra M. It doesn't matter what kind of algebra it is at this moment. Then there are at least three natural equivalences between them by which we could try to classify these Masas sitting in M. First, we could classify them up to inner conjugacy. That is listed here, one. And of course, two such Masas are inner conjugate in M if there exists a unitary element in the ambient algebra M, which maps such that conjugation by that unitary maps one of these subalgebras onto the other. So in other words, two Masas A and B are inner conjugate in M if there exists an inner automorphism of M, which maps A onto B. Second equivalence could be called, I would say, conjugacy, but somebody could say outer conjugacy. So two such Masas are conjugate if there exists an automorphism of the ambient algebra M mapping one of these subalgebras, say A, onto B. So of course the difference is that here this alpha could be an outer automorphism and not necessarily inner, as in the previous case. Now, finally, we could kind of weakest notion could be if we just ask for an algebraic isomorphism or star isomorphism, if you like, of these Masas. And in this third case, this first case doesn't see at all the ambient algebra M. Here we just ask if A and B are abstractly isomorphic by perhaps some isomorphism which cannot be extended to the ambient algebra M. Okay, I guess there could be some other ways of classifying Masas of an algebra, but for me, these sort of most natural ones. There are obvious implications that, you know, 1 implies 2, 2 implies 3. This is completely obvious. In general, again, this is easy to believe. In general, these implications cannot be reversed. However, there are instances where this implication could be reversed in some special cases, but in general, of course not. This cannot happen. So maybe before moving forward, some additional comment to that. So here, I mean, I talk about Masas because that's the main subject of paper with Tomohiro and Jonki that I alluded to on the front page. I mean, discussing the title and of this talk and co-authors. But of course, these 3 types of classifications make sense for any other subalgebras of this ambient algebra M, not necessarily a Masa, not even necessarily an abelian subalgebra. And one could talk about, for example, similar classification for Cartan subalgebras, or one could talk, which is a very famous and broadly developed area, one could talk about such classification for subfactors in factor von Neumann algebras. That is, we talk about John's index theory and so on. So of course, it's not necessary to stick to Masas here, but I just did it because that's these are the main objects regarding which I will have some concrete technical results that will be mentioned at the end of my talk. Also, before moving forward, okay, so now to be more specific, I said star algebra M here, rather not very concretely, but I mean, well, I'm operator algebraist, so I primarily think of M as either C-star algebra or von Neumann algebra, and it's completely obvious that and well known that these sort of classifications are much better developed in the context of von Neumann algebras. This work on classification of Masas in von Neumann algebras, in particular factors, has been going on for a long time, and there are numerous results which I'm not going to go into at all, except for briefly alluding something in a few minutes. And this is due to work of many hands. There are spectacular results actually in classification of Masas in Cartan subalgebras, so factor von Neumann algebras. And by comparison with von Neumann algebra theory, the situation with C-star algebras does not look that rosy at all. That is, results about classification of Masas in C-star algebras are actually scarce. I mean, they are not that numerous, at least to the best of my knowledge. And this is probably due to the fact that it's much more difficult to classify a Masa in some large C-star algebra. I mean, what I have in mind, we'll come to that later, but I have in mind classification of this kind of objects in purely infinite graph C-star algebras, like say Kunz algebras, ON. So in this setting, such a classification is not inside, not at hand. I mean, not visible yet. There are some results that we can already talk about, but it's very far. Situation is very far from the kind of results that people obtain regarding conjugacy of Masas in factor von Neumann algebras.
Wojciech, if I may ask you just a silly, naive question.
Yes, go ahead.
Does this classification of Masas help somehow in the classification program of C-star algebras themselves?
No. I mean, I don't know actually of such applications. If there is an expert in the audience who could correct me, then please go ahead. But I myself am not aware of such applications. I cannot recall that this kind of thing would be used in any substantial way. You know, classification of sister algebras went in a different direction along, you know, Elliott's program by, you know, K-theoretic invariants built from the sister algebra, and I cannot recall that it would be used. However, I should say that this is, again, not what I'm going to talk here, but recently there have been quite strong results, in particular by Xin Li, but also by other people, about existence of Cartan subalgebras in sister algebras. And there is a possibility of relating this question to questions about UCT problem and so on. So from that point of view, yes, I cannot recall, you know, appearance of this kind of classification in the within the Elliott program, but yes, there have been very nice results recently, as I said, about Cartan subalgebras in sister algebras. However, this is somewhat aside from what
our joint friend and colleague Soren. He uses graph sister algebras in the classification program going beyond simple sister algebras. So somehow.
That's right. That's right. So I mean, okay. I understood that what you ask is about, you know, classify simple sister algebras, but there are other questions. Now, these. It's somehow these Masas become, play important role when you, for example, relate sister algebras kind of to dynamical systems. And it's actually people exactly like Soren Eilers and others look into the question whether, for example, two sister algebras are isomorphic in a sense that maps distinguished massa on one of them onto distinguished massa on the other one, right? So this is an important question, and it obviously relates to this kind of classification. Yes, that's correct. So this is true that actually there is interest in looking at this kind of pairs, sister algebra and some distinguished massa sitting in, and looking at kind of isomorphism class of that pair. Yes. So it's actually, in a sense, it is directly related to what I'm talking about. But I will not take that angle. I will not take that angle.
Thanks.
Okay. So actually, my small motivation for looking. Okay. So there are three problems here. So let me be more specific. What I'm particularly interested in, in the following question. Given two massas which are outer conjugate, that is for which there exists an automorphism mapping one of them onto the other, are they also inner conjugate? That's the kind of key question that I ask in this context, and would like to try to answer it as far as I can. So that's the kind of, for the purpose of this talk, this is the kind of question that I would like to pose. Given two outer conjugate massas, can we determine if they are also inner conjugate? Okay, and why am I interested in that question? So we can go to the next page, because of this question has some relevance to the problem of understanding the outer automorphism group of our algebra M. In the following sense, so outer automorphism groups for large sister algebras like Kunz algebras are, of course, these some kind of monster groups that are very difficult to grasp, and I'm not saying that we are close to understanding exactly the structure of such groups. This is again by contrast to many cases of factor von Neumann algebras. Already long time ago, due to work of Alan Kohn, we got quite amazing insight into the structure of outer automorphism groups of factors. But in the case of sister algebras like ON, we are very, very far away from really understanding these groups. Even such questions, like, is it simple or not? I mean, okay. So, but coming back to the motivation that I have in mind here. So, okay. So suppose you will try to understand outer automorphism group of your favorite sister algebra, for example, O2. I mean, of course, outer automorphism group is the group of all automorphisms quotient out by the inner ones. So one possible strategy of gaining some insight here, making some inroads, would be choose your favorite massa A of M and do two things. First, analyze the image in the outer automorphism group of the group of those automorphisms which globally preserve this massa. And second, try to understand how other automorphisms move this massa around. And since you are interested in outer automorphism group, you are only interested in how automorphisms move massas, but modulo inner conjugacy. So if one were able to somehow answer these two questions, then that, in my opinion, would constitute a very big step towards understanding the structure of the outer automorphism group of M. Now,
but if I may, again, a silly question.
Go ahead.
Is it possible that you have an automorphism of your sister algebra for Neumann algebra which is outer from the point of view of the sister algebra itself, but happens to be inner when you restrict it to massa?
Absolutely, because it could be on that massa, it could be identity, for example.
Okay,
I mean,
surely. Yes.
That's not a problem at all.
Yes. Okay.
Okay, so just to give some more concrete, add something more concrete to this very general strategy. Actually, some work going a little bit in that direction has been done already with regard to graph algebras and in particular Kunz algebras. In particular, I mean, it was already Joachim Kunz who looked carefully and obtained nice results about the structure of this group for ON, where A, of course, was the standard diagonal massa in ON, Dn. Understanding its image in the outer automorphism group, that's more complicated, but quite a lot of work actually in this direction has been done. I mean, this is related to the so-called the Weil group of Kunz algebra, and in particular, I mean, many years after pioneering work by Joachim Kunz, it was Roberto Conti and myself that we started looking into this question. And then some other collaborators joined in. So we actually, I mean, I cannot say that we fully understand this situation in the case of ON, but there is quite substantial progress had been made here. Much less progress has been done on that side here of understanding. So here we are more advanced. And we are less advanced here, and my talk is somehow aimed at showing some possible approaches to attacking this second question. Okay, so now I would like to start moving maybe indicating some concrete things. As I said. von Neumann algebra theory is much more advanced. So maybe let me say a few words about the von Neumann algebras, even though I'm not a von Neumann algebra person. So I will be brief, and I just want to indicate something. So there are some invariants actually on in the framework of von Neumann algebras, factor von Neumann algebras, that allow us to distinguish Masas, in particular, not going into detail. Long time ago, there's Pukański's invariant appeared that was used in great success in the context of type 2 factor. That invariant is computable. It's a subset of the set of natural numbers enlarged by infinity. I will not go into details, but just to indicate that there are computable invariants in the von Neumann algebra setting. For me, actually, more interesting is certain technique that I would refer to as Popper's intertwining by modules technique. And again, it's valid in the von Neumann algebra setting. I mean, as stated here, a trace appears, so it works in the type 2. One case, I mean, but it's been extended to type 3 case as well. I mean, again, I mean, von Neumann algebras, this is not what I want to talk about, so I will not here read it for you, but just I would like to point out the idea. So the idea here is that we look at two subalgebras of our von Neumann algebra M, and we are interested in if a corner of one of them could be mapped onto a corner of the other one of them by an inner mapping, that is mapping implemented by partial isometry. I mean, not to complicate things, I mean, you could ask easier question whether these two subalgebras are conjugate by unitary inside M. And it turns out, so this is a question that is essentially, we are talking about some conjugacy issue. And it turns out that this could be, that this question could be somehow answered by looking for sequences of unitaries in one of these subalgebras with the following property, that if you apply conditional expectation onto the other one of them, two elements of that sequence multiply on both sides by arbitrary elements from the ambient algebras, and then you look at the tracial norm of this conditional expectation of that element, that if you have control of what happens to the tracial norm, that in particular if it goes to 0 for arbitrary x and y, then such an embedding cannot happen. In particular, if you can find such a sequence, then these two guys, A and B, are not inner conjugate. So, I mean, of course, this is purely von Neumann algebra technique, and it cannot, does not translate into sister algebra setting at all, but it has some interesting aspects, namely this kind of convergence, looking for sequence of unitaries satisfying this kind of convergence property, of course, makes sense in a sister algebraic setting. What we need certain ingredients here. We need conditional expectation, and we need trace. Notice that this trace tau does not have to exist on the entire algebra M, because you apply it only here, you apply it only on B, so that tau actually you need only on B.
May I have a question?
Yes, go ahead.
About this first point, this invariant, so it is defined for any 2-1 factor, or maybe only for this
for 2-1 factor. I mean, you go to standard form of the 2-1 factor, and then you do. I don't want to go into details, and then you calculate. Yeah.
But this is something which carries some information about a massa, but does it also carry some information about the factor itself?
Well, it allows you to distinguish non-conjugate massas because you calculate that invariant for two massas. If you get different, then they cannot be conjugate.
No, what I'm having in mind, so it could possibly, maybe, it could happen that, for example, for the hyperfinite 2-1 factor, if you investigate each massa of it, you
yeah, sure, of course. But I don't have these results in my head right now. But yeah, sure. But this is long story. I mean, the Pukański invariant. This is invariant known for a long time. So specialists in von Neumann algebra theory, I think they already utilize it, to large extent. I just brought it up here to indicate that in von Neumann algebraic setting, there are computable invariants of that conjugacy. This invariant is not applicable to sister algebra. In particular, I should point out that Pukański invariant that cannot translate to sister algebras because you do this calculation, you have to take a standard form of this factor and do some calculations with cutting, projection, and so on. So this is definitely von Neumann algebraic technique. I don't know how this could be translated into sister algebras, for example. So what I want to emphasize that this kind of thing, that this convergence, this is something that one can compute it in a sister algebra. And this is exactly the kind of method that I would like to, I will be a little more precise in a moment for sister algebras, but it is actually this kind of a convergence result that I would advocate as a good way of trying to answering this question of our inner versus outer conjugacies of subalgebras of sister algebras. Okay. So let's move to sister algebras now. I said a bit earlier that the results are scarce and there is not that much known. Well, of course, there are some results, and in particular, the situation is not so bad when it comes to AF algebras. So, for example, it is known essentially from the beginning of the theory of AF algebras that any two standard diagonals in an AF algebra are conjugate, even though they may not be inner conjugate. So that, I mean, this is an example of a kind of general result in this direction that is known. And in general, much more results in this kind of spirit are known for finite von Neumann algebras, as far as I can tell, not quantifying that statement, and much less is known when you go to infinite, especially purely infinite sister algebras.
Wojciech, again, if I might, could you remind me, please, what diagonals mean?
Well, okay, so I mean, AF algebra is built from finite dimensional sister algebras, from matrix algebras, and in a matrix n by n matrix algebra, you have diagonal, simply diagonal matrices. So in a direct sum of such finite matrix algebras, you have canonical diagonal. And when I say standard diagonals, I mean by going in this approximation higher and higher up, by taking these diagonals together, you will get actually a diagonal massa in AF algebra. That's what I'm referring to. I mean, there are some technical definitions of what a diagonal in a sister algebra is, but here I'm using in this obvious sense how you construct an AF algebra from increasing sequence of finite dimensional sister algebras.
Okay, so if I understand you correctly, for AF algebras, there is this obvious definition or construction, and you can refer to it as standard. But if you have an abstract sister algebra, can you still speak about diagonal massa?
Yes, you can speak, yes.
Okay.
Yeah. Yeah, that's what I said, that you can speak, but I'm not.
Okay, I can. Okay, gotcha. Thank you.
Okay, so my second point I already made, here on this slide that for purely infinite simple sister algebras, there's not much that is known. I mean, again, if someone can correct me, then please go ahead, but I'm not aware of many dramatic results in that direction for purely infinite simple sister algebras. However, and now I want to come back to that Popper's trick. This convergence business can be used in an obvious way in the situation of purely infinite simple sister algebras. Just imagine that M is such a big sister algebra, and suppose that you have two AB subalgebras, and now all you need a conditional expectation from M onto B, and you need a trace on B, and this can very well happen. I mean, just think of Kunz algebra, and you can think of B either standard Massa in ON, or you could think even of the UHF core subalgebra or something like that. So this can easily happen that you have in your disposal both such conditional expectations, such a trace. And then if you have such a sequence of unitaries in U, such that this convergence takes place for all x, y in the ambient algebra M, when recall here phi b is this conditional expectation, and this 2 indicates the tracial norm with respect to this trace T, then you cannot find a unitary V in M that would give you this embedding for this, because of this obvious calculation. So I would like to call this condition here, which says that there exists such a sequence of unitaries which does this. I would like to call it condition star. One could even say red star, but I will just call it condition star. Maybe it's better.
Yes, I have to clarify one thing, Wojtek. You see, our channel is marked as not containing any advertisements, and this looks to me like Heineken. You have no connection, no?
No, but you see, this didn't occur to me. So no, I'm not. Actually, I don't drink Heineken. So I definitely say that you are on a false. This is false here direction.
Okay.
No, it's definitely not Heineken.
But I like beer, but
yeah, I drink. Actually, Belgian beers are higher on my list. So yes. Okay. No. So this has nothing to do. This has nothing to do with Heineken. Okay.
Good. Just
so
have to double check.
In short, what I would like to say, and what is actually the main point of my paper with Tomohiro and Jonki that we put on the archive not that long ago, is that this condition star actually works well, and we believe it's actually something that you can check. I mean, okay, we didn't check it, for all sister algebras and full generality and so on, but we have gathered, I believe, sufficient evidence that indicates that this is something that you can work with. Okay, it is maybe not a computable invariant, but it is a technique that you can verify. You can verify whether this condition holds or not in concrete situations working with non-trivial objects. And this I will come back to concretely a bit later. Okay, so this is again essentially my talk is about advertising for this technique. When you want to answer this question, are two Masas in some big sister algebra are the inner conjugate or not? Okay, so I actually want to talk about graph sister algebras. Now, I understand that most people in the audience are probably experts on graph sister algebras, but nevertheless, I felt that maybe it's better to recall some definition, in particular set denotation. Okay, so I will denote usually graph by E. This is a directed graph. We'll have some set of vertices, edges with range and source. And then a graph sister algebra is the universal sister algebra generated by these projections and corresponding to vertices, and partial isometries corresponding to edges, satisfying these famous relations. Now, I should point out that, of course, this could be very general. These graphs could be infinite, blah, blah, blah. But for the purpose of this talk, you should think of a finite graph in which there are no sinks, no sources. The graph is transitive, and every cycle in the graph has an exit. So in other words, a finite graph such that the corresponding sister algebra is purely infinite density.
What does it mean, transitive?
That there is a directed path from any vertex to any other.
Oh, okay, so it's stronger than connected. It's kind of like path connected.
Yeah. Mm-hmm. Okay, but in short, I'm talking about unital sister algebras corresponding to finite graphs, which are purely infinite density. Yeah, that's ON, for example. If you don't like graphs, you can think of ON, and in that case, that graph will be just one vertex with n edges attached to it.
But you can also think SUQ2, I think. Oh no, because there's a loop which has no exit.
SUQ2 is not transitive. You see, for SUQ2 you have two vertices, but there is no path going. However, that would be also okay. That kind of graph would also be okay for the purpose of my talk, but it's not simple. The sister algebra is, of course, not simple.
Of course.
Okay, so what will be important for me is the canonical object sitting inside. First of all, you have the core AF subalgebra of such a graph algebra, which I'll denote F sum E, which is a norm closure of such expressions, where here alpha and beta are words of the same length. So this is the fixed point algebra for the canonical gauge action of the circle group on the graph algebra. And inside FE, inside this core AF subalgebra, you have the standard canonical massa in graph algebra, which is generated here by these range projections of these partial isometries of S alpha corresponding to words. Okay, so this is, I will refer to the standard diagonal or standard massa in the graph algebra. Okay, let's. I hope this is quick, but I hope it's acceptable here in this seminar. Since I want to keep in perspective also, what kind of automorphisms we can look at. In particular, it's good to have in mind a certain construction of which works on the more general level than automorphism, because you can construct unital endomorphisms by this. So this is Kunz construction. Kunz gave this prescription as prescription for all unital endomorphisms of ON algebras. This technique, this method applies also to graph algebras. However, in the case of general graph algebras, it does not yield all unital endomorphisms, only certain interesting subclass of that. So, okay, how it goes. So here, to construct such a Kunz type endomorphism, you have to start with a unitary, but not in an arbitrary unitary. You have to take unitary which commutes with the vertex projections corresponding to vertices of the graph. So that's the restriction. In the case of Kunz algebras, this is no restriction, because there is only one vertex projection there, which is identity, so everything commutes with that. But for general graph algebras, this is a restrictive condition. And then you can, and then given such a unitary, you construct the endomorphism of the graph algebra by simply multiplying on the generators by fixing vertex projections and generating partial isometry corresponding to edges by that unitary from the left. Now, this prescription, of course, it assigns only values to generators, but by universality of the graph algebra, it extends to a unital endomorphism of the graph algebra, which fixes all vertex projections. And
Wojciech, just to make sure, sorry to interrupt, just to make sure, you called it endomorphism, not because it's not bijective, because it is bijective. You can multiply.
No, it's not bijective. That's the point.
It's not bijective. So what's wrong with multiplying by a star?
Bijective. I mean, typically it will be injective, but it does not have to be surjective.
Ah, it does not have to be surjective. Okay, yes.
I mean, example to keep in mind is the shift endomorphism, which I will actually mention in a second. I mean, so that's the point, that we are talking here not only automorphisms, but endomorphisms. Okay, I cannot say for all unitaries and all graph algebras, but say if you think of Kunz algebra, then every such an endomorphism is automatic. Okay, if we are talking about you know, purely if you are talking right. So I mean, okay, let's leave it. For example, for Kunz algebra, so every such an endomorphism will be automatically injective, of course, because it's a homomorphism of a simple sister algebra, but it doesn't have to be onto. That condition of being onto does not need to be satisfied. Shift, for example, I mean, it does not.
Yeah. Thank you so much. This was an important clarification. Thank you.
Okay, but I'm more interested in automorphisms. Okay, I'll just display entire page. I think this is my entire page here, and I will talk to it. Okay, so here I listed some examples, typical examples of automorphism. Now I'm talking automorphisms of graph algebras that we have in mind. First of all, you have a class of automorphisms obtained by this Kunz construction that is given by this prescription that I just described above. As I said before, in the as shown by Kunz, right, in his famous paper from the 70s, if C star of E is a Kunz algebra ON, then this is all. Every automorphism is of that type. But for arbitrary graph algebra, this is not the case. This is just some subclass. Now, notice that here you could look deeper into these automorphisms, and you could look at certain classes of them depending on the choice of type of unitary here. And two choices that have been particularly investigated is first so-called localized automorphisms, which correspond to choosing U in the here FEK. What is FEK? These are elements of the finite dimensional part, so to speak, of the core AF subalgebra of the graph algebra. That is unitaries that can be written as a finite expression as in terms of generators on the graph algebras. Now,
and this K refers to what? To the number of generators?
K, remember, to the length of paths that I'm using.
That's what I thought, yes.
Yeah, K refers maximal length of paths that I'm using.
Yeah.
And now a very special case of those localized automorphisms. Notice that in this case, if U is in FEK, this still can be proper endomorphism. This doesn't guarantee that it's automorphism. You still have to check if it's invertible. However, if you take K equal to 1, then every such an endomorphism lambda U with U in FE1, of course, commuting with the vertex projections, is automatically automorphism, and it is called quasi-3. These are the so-called quasi-3 automorphisms of the graph algebras. I will actually, one of the results that I will mention at the end will pertain those quasi-3 automorphisms. So these are specific automorphisms of the type lambda U when U is a unitary in FE1.
And will you explain why they are called quasi-3?
Well, I mean, this terminology, I mean, it has something to do with quantum physics, and it was invented. I believe it was Evans, I believe, who maybe Paul Baum can correct me if he listens, but I believe it was David Evans who introduced that terminology. It refers to I mean, it has roots in physics, this terminology.
Sometimes they are also called Bogoliubov automorphisms.
Sorry, I couldn't hear.
Sometimes they are also called Bogoliubov automorphisms.
Exactly. Oh, Roberto. Ciao, Roberto. I didn't know that you were. Yes, that's right. That's right. Going even deeper to physics, some people would call them Bogolyubov automorphisms. Because I mean, I will not go into that. But but am I right, Roberto, that this was David Evans who called them first like that? I think this is probably correct.
Well, it's not so clear to me, but certainly Evans used the terminology.
Oh, okay.
Difficult to trace back who was.
Yeah, okay, all right. But he was one of the first who used it, certainly in papers long time ago, right? Okay. So going back to these special classes of automorphisms, I mean, another much smaller class, but also interesting, if you have any automorphism of your graph, then it obviously.
Can I just say one very...
Yeah, go ahead, Roberto, please.
Maybe the terminology was taken from automorphisms of the car algebra.
Yeah, precisely.
Yeah, that were
precisely. That's what I had in mind. This is exactly
in physics. So
yeah, I'm pretty sure. Yeah, that's probably was the case. Yes.
Taken from there.
Good. So coming back to these other classes of typical classes of automorphisms of graph algebras, then every graph automorphism in an obvious way leads to an automorphism of a graph algebra. And notice that these are definitely not of this type because they move. Or they can move at least vertex projections. So automorphism like this, graph automorphism, typically will not be of this Kunst type. Then, of course, you have great many of inner automorphisms of C star of E, which could be of neither of these types. And then perhaps you could even have some other exotic automorphisms, but it's not clear to me if they always exist or not. I mean, at least these three are some kind of obvious candidates to look at if you are interested in automorphisms of graph algebras.
Sorry, Wojtek, another nice question.
Yes, go ahead, please.
If you would all of a sudden, out of the blue, started demanding let these automorphisms preserve a gauge action, how would the picture change?
If they preserve the gauge action, well, then they would preserve the AF subalgebra, and I would have to think a second. In the Kunst algebra, that would imply that U actually itself has to be in this AF, or in the Kunst algebra case, core UHF subalgebra. I'm not sure if that would immediately that would not imply the same for all graph algebras, right? But for Kunst algebra, that would simply lead to the fact that U must be immediately in this core UHF subalgebra of yeah. So that would have implication on this automorphism, very strong implication.
I ask because it's always very important when you study graphs and graph algebras whether the morphism you've got are equivariant with respect to the gauge action or not.
That's right. I mean, these are particular nice. These are particular nice and more accessible.
Yes. Exactly.
These are particular nice and more accessible. Yeah. Okay. So I'm not sure actually how I'm doing for time. Am I doing okay for time, Piotr? Or?
Well, you still have 41 minutes.
41 minutes. Yeah. Oh, gee, maybe I finish earlier. I don't know. It depends how many questions you ask. But let's see. When I prepared my talk, I left time for 50 questions from the audience and 200 questions from the organizers. So we still have some room. We still have some room there.
Okay. So you can take it slowly.
Okay, so now I'm actually coming to the final part of my talk. As a matter of fact, that is, I would like to, without I hope too many technicalities, briefly just outline two results from the little paper that I'm talking about. So one result will be actually for Kunst algebra, and only the last one that I'll mention in a second will have something to do with more general graph algebras. it's very good that Roberto is here with us today, because in a sense, this story started from a paper that we wrote with Roberto and Jonki some time ago. And in that paper, we looked exactly on the case of Kunz algebras. And we argued that if you take an quasi-3 automorphism of a Kunz algebra, which moves the standard, the canonical diagonal Masa, then the image under that quasi-3 automorphism of the diagonal Masa is not inner conjugate to the diagonal Masa. That is, it's enough that it moves a little bit the diagonal Masa. Quasi-3, once again, very special automorphism, quasi-3, and the image automatically cannot be inner conjugate to the diagonal. That started it, and I should say that the proof that we gave, actually very, in my opinion, short and elegant proof of that fact, was a precise calculation, which, sorry, I hope Roberto doesn't mind my saying, that was a little bit ad hoc. Ad hoc in the sense that we look at the situation at hand and we produced a nice self-contained argument that proved the case. But it was not immediately obvious, at least to me, it was not immediately obvious how that argument could be generalized to much greater class of examples. I don't know. Do you agree with that, Roberto, or you don't agree?
You have to unmute. Yes.
I agree.
Okay, I don't want to offend anybody, so I'm not saying anything wrong about that, but it was the first step in that direction. It was nice argument. It was different. It was not that argument that I advocated here. And later with Tomohiro and Jonki, and also Sophie Mikkelsen, we checked that this condition star technique actually can be also used to prove that. And then, right, we observed that this case can be generalized, not just to, quasi-3 automorphisms, but in a sense, we forgot for a moment automorphisms, and we just look at some class of Masas in ON, which by direct application of this condition star method can be shown that they are not inner conjugate to the diagonal Masa. This class contains all those that are produced by moving diagonal Masa by a quasi-3 automorphism. So that case that I mentioned before, that the image under quasi-3 automorphism of a diagonal Masa is not inner conjugate to diagonal Masa if it's different, it's a very special case of that result that I will mention here.
Wojciech, could you perhaps write this result which you mentioned about quasi-3? I have visual memory. If I don't see it written, it's hard for me to remember.
Well, I cannot write it here. I mean, it says that if you, I can actually, if I scroll down, actually, then I will show you what I meant. Okay, so if you look at this theorem, instead of D here is for graph algebras, but okay, it also applies to Kunz algebras. So here, lambda, if you take U unitary, which gives rise to a quasi-3 automorphism.
Yes.
If
so
that automorphism moves the diagonal Masa, that is, if the image is just different, if at least one element goes out, then this diagonal Masa and the image under this quasi-3 automorphism are not inner conjugate.
Okay, I've got you now. Yes.
So this is, I stated here for graph algebras, but the same applies to Kunz algebras, and that's the result I refer to.
Okay, so you generalize your work with Roberto.
Roberto and Jonki.
And Jonki, yes.
Okay, so going back to where we stopped. So here there is first, before stating it, actually a little bit reduction. So I'm trying to, I want to take some Masa in ON, which is different from the diagonal, okay, I don't care at that moment whether it's obtained as an image of some automorphism. I just take another massa of ON of a special type, and I ask myself, is that new massa inner conjugate to the diagonal one, the N?
Sorry, Wojtek, because there are students also, at least one student in the seminar. Could you recall the graph of ON, just how it looks like?
It is one vertex with N edges attached to it.
Okay, good.
Okay, so my question that I'm asking here is like this. I'm going to take some, not arbitrary, but some specially constructed massa, a class of massas in ON. And I'm going to ask a question, is that massa inner conjugate to the diagonal, the N? And I want to find a condition which would tell me that it is not. And that condition, of course, will be my condition star. So I need to cook up situation in which I can verify that this condition star holds for that massa A. So first of all, I want to show some simple reductions. So first of all, in the case of Kunz algebra, this condition star, it suffices to verify. I mean, here, instead of this and this, you should have some arbitrary elements X and Y from the C-star algebra. By density, it's enough to look at these kind of generating partial isometries. This is first, this is obvious. And then the next step you could do, you could decompose your unitaries that you are going to work with. You can do the Fourier series decomposition for each of these unitaries. And then it's also not difficult to see that verifying condition star can be done independently for each component, that is for each component with respect to the Fourier decomposition of the unitary, right? So it breaks along these M's, right? So this just shows that in this case of Kunz algebra and actually also in general graph algebras, verifying that condition star, I mean, it's still difficult, but it can be simplified somewhat. Now,
wait. So you're saying that all this reduction happens for any graph system algebra, not just
well, I want to be a little careful, so I'm stating them only for Kunz algebras right now, but similar reductions could take place also in graph algebras. I'm not saying exactly the same for arbitrary graph algebras. To be careful, I'm just stating this right now for graph algebras, but not for graph algebras, for Kunz algebras. But for graph algebras, similar methods could be also used.
So I understand that this one can be different, but I think doesn't this follow from just the basis theorem for graph system algebras?
From what? Sorry.
Basis theorem. You know what is a linear basis? Schauder basis.
Well, the previous one.
Yeah.
Okay, here, but sorry. Yes, this previous one, yes. But here I have also some restrictions on alpha, beta, mu, and so this you have to do something. So it's not just.
Yeah, I agree. So the previous one was for arbitrary.
Yeah, just. And but then through some manipulations, you can further reduce it. So here, what I'm saying is that this verification, I don't want to, I mean, this is becoming very technical, but what I want to say that this verification, whether this condition star holds or not, can be reduced somewhat from, you know, checking for arbitrary elements X and Y. It can be reduced to certain more, you know, much more restricted situations. Okay, that's what I wanted to say at this moment here.
Wojtek, if I might suggest, it seems like we are after sunset in Denmark. Can you put some light on, because we don't see you anymore?
Well, but why do you need to see me? I mean, it's okay.
Much better. Because we like.
All right. So now the construction. I mean, this is again becoming a little technical, but. Okay, instead of reading this slide, I mean, what is the idea? Okay, just imagine we are talking ON. So notice that the core UHF subalgebra, you can think of this as an infinite tensor product. Now, the theorem that I already mentioned about quasi-3 automorphisms moving to diagonal massa, how does it work? Quasi-3 automorphism moves a little bit diagonal in each matrix algebra factor of that infinite tensor product. And then that's how you get it. You get it, this quasi-3 moves, it's a product type automorphism of this UHF subalgebra, and it rotates a little bit in each factor. So what this construction here that I wrote, I will not read it, what it does, it generalizes that situation to the following case. Instead of looking at the individual matrix algebras Mn in that tensor product, you can group them together in blocks, and you can move each block a little bit by a unitary. So that's essentially the construction. Instead of rotating by the same unitary, inside each factor Mn, you can rotate by different unitary blocks of Mn tensor few times and Mn. Now, if these additional technical conditions are satisfied, then this rotation taken together will rotate diagonal massa into another massa of the Kunz algebra, which by condition star is shown not to be inner conjugate to the diagonal massa. So in a sense, it's actually, conceptually, it's quite straightforward generalization of that result for quasi-3 automorphisms. However, I'm not sure if a direct argument would be so easy to carry out. On the other hand, that condition star works. Perhaps you may say that this example is cooked up in such a way that that condition works. In a sense, yes. But on the other hand, it gives a huge class of massas of ON, which are not inner conjugate to the diagonal in a kind of very relatively easy way. You have to do some work here, though. Okay, so
Wojciech,
yes?
Sorry, do I understand it correctly that in order to have this condition red star satisfied, so that you know that these massas are not inner conjugate, yes, you must pick up an appropriate sequence of these unitaries which are different at every block, right? So that's right. That's the idea, that you have this freedom to choose whatever you want at every block, and then if you choose it right, you will get this condition red star satisfied.
That's right. And this is on my next. This is on my next slide. This is how you choose these unitaries here. So I didn't scroll to the next slide. So. Because here I was explaining how I construct this family of these new massas, and here is exactly what you said, Piotr, that you have to choose these unitaries, and this construction was such that this natural choice of these unitaries works.
And what is DJ here?
Well, I said I didn't go over all these details. You see, this guy here.
Yeah, decay.
Yeah, this is these guys here. This is a K, denoted K here. It's the same.
For which K let decay be a unitary? Okay. Mm-hmm.
Yeah. Sorry. This is really a bit technical, so I think maybe I will move on. But the main idea is that this result.
Can I ask you a question?
Yeah, go ahead, Roberto.
Is the Fourier series of this WK finite? So only a finite.
Sorry, say again. I couldn't hear you. Say again.
Before you had the formula for the Fourier series, and you wrote that WK is the sum of.
Yeah, it's a big. It's in the core. Yeah.
But is it finite? So it's in a finite dimensional subalgebra.
Yes. But these WKs are in the UHF subalgebra. So the Fourier series is just one element.
There is. Okay, can I see a couple of slides before? There was some formula.
The Fourier series is just W0. WK only m equal to 0.
Okay. So
no, it's the trivial case when everything sits in the UHF subalgebra.
Mm-hmm. Okay, so this formula refers to a more general situation.
Yeah. I started in a more general setting to show because I did some other calculations. You can apply it, in more general setting. At first, I wanted to show that some reductions are possible, but then this particular theorem, I have m equal to 0 only.
Okay.
That's the Z gradient coming from the gauge action. So if
Of course, these are the
invariant.
spectral subspaces of the gauge action.
Exactly.
All right.
Yeah, sorry if I didn't. Okay, that's right. The first was something a bit more general, and here is a bit more specific.
Mhm.
Okay, so the second and the last result that I would like to mention. So now we finally deal with this fairly general setting of graph sister algebras. Once again, these are correspond to finite graphs, transitive graphs. Every cycle has an exit, so corresponding sister algebras are pure infinite simple unital. Now, this result we actually proved only for quasi-3 automorphisms, but we are talking now not just Kunz algebras, but general these graph algebras. So we take a quasi-3 automorphism of such a graph algebra, and we claim, analogously to the previously mentioned result for Kunz algebras, that if such a quasi-3 automorphism moves the standard diagonal massa at all, if it moves it at all, then the diagonal massa is not inner conjugate to the image under this quasi-3 automorphism of this diagonal massa. So this is the extension of that result that I mentioned before due to Roberto, Jonki, and myself for graph algebras. Now,
sorry about that. Could you please explain the notation? I'm confused here.
Which part of notation?
This one.
DE0 is the set of vertex projections. This is vertex projections, or rather span of the vertex.
So that's this condition that you must
so
commute
this
with
is
vertex
condition which
projections.
says that unitary which commutes with vertex projections.
Okay, this was.
And in FE1, that gives rise lambda u is quasi-3.
Exactly, that's this I remember.
Is that clear now? Okay.
Yeah. Mm-hmm.
Okay, good. So.
Read this theorem. You are not inner conjugate, but you still might be conjugate.
Well, they are conjugate because lambda
of
u
course,
is.
Yes, of course. Sorry, by construction. Sorry.
So these are two massas that are outer conjugate, but not inner conjugate.
Yeah. Yes, sorry, of course.
Okay, and I should mention. I will say a few words about the proof. I mean, the proof is, again, as you can guess, I will say in a second that I can apply this condition red star, but this result is actually not new because it was proved in an earlier paper due to Tomohiro, Jonki, and my former PhD student, Sofia Mikkelsen. But again, in that previous proof of that result, we used an ad hoc argument. We used an ad hoc argument modeled by the proof from the case of Kunz algebras, which was cooked up for these quasi-3 automorphisms and so on. And it was okay. But what we provided here in the preprint that I'm discussing right now, we verified that this condition red star also, which is quite different. Okay, I didn't tell you anything about that, what I refer to ad hoc argument, but it was very different. Okay, very, at least at the first glance, it was quite different from the condition red star that I mentioned here. So in the present paper, we verify applicability of this condition red star in this situation. We wanted to do so because, as I said, we are trying to develop some method that could be fairly general and could be applicable in hopefully many other instances. So we are kind of, first of all, building some class of examples, but also learning how that technique actually works, how to make it work. I mean, it is not something that you punch two buttons and you get the result. I mean, it's a technique, but it requires quite substantial analytic work to actually implement it in concrete situation. And this is what we are aiming at. We are aiming at developing machinery that becomes smooth in such a way that you know how to turn it on, how to run with that machine in many interesting situations. That's what I'm advocating, because someone can say, okay, that theorem was already known. This is not what I'm advocating. I'm advocating a new approach, new method that, of course, it proves this, but it proves many other things. And hopefully it can be polished and developed into well-functioning technique.
Wait, just to clarify, when you say this theorem is already known, which theorem?
Well, as I said, it was proved by different methods earlier.
You mean this one, right? This theorem?
That particular one, yes.
Okay.
Was proved already earlier in an earlier paper of several people, including myself, by a different method, by an ad hoc technique.
Yeah, and you
So
have a
in
systematic
that case,
approach.
the main point here was to show that actually this technique that I'm advocating here, this condition red star, is actually applicable here. Now, I want to go actually to this and make some comment about that. So the technique works like this. First, you consider a shift on the graph algebra, the usual shift, but you have to notice a few things. This is a unital and completely positive, right? Is containing its multiplicative, but you have the, okay, so these unitaries that give rise to quasi-3 automorphisms are contained in the multiplicative domain of the shift. It means that that they sit in the sister algebra on which that shift acts as star homomorphism, actually. Okay, and then you have to, the key point is, okay, you take a unitary in the DE1, which is moved by a unitary U outside of the diagonal, and then you kind of iterate it by the shift and take your WK as this kind of product, which also can be seen in this way. So notice this is somewhat similar construction to what we did above here. This is somewhat similar to this method. In particular, if here I was talking about the quasi-3 situation, then I would be more or less in a very similar situation. Okay, so this choice, so essentially what we show in the proof, we show that for this choice of a sequence of unitaries, condition star can be verified, and therefore we get the result. Now, I have, this is not the place, and I have no time and no intention of going into technical details how that verification of that condition star can be done. I refer interested persons to the preprint. However, I should point out that this is non-trivial, that actually to verify this condition star for that natural choice of these unitaries is technically not easy and requires some ingenuity and a little careful estimates. And I would like to point out to a source of difficulty. Now, if you recall, you need to work with a trace. I mean, this condition star is phrased in terms of tracial norm, So which trace you are using? In case of, ON algebra, there is a canonical unique trace on the UHF core subalgebra of the Kunz algebra, and that trace you are using. This is not so. There is no such unique trace on a graph algebra in general. So here we are using the canonical, I'm referring to it as a canonical trace, or if you like, the Perron-Frobenius trace. So the trace on the core AF subalgebra given by the Perron-Frobenius eigenvalue for the adjacency matrix of the graph, right? So A here is the adjacent. Okay, sorry for clash of notation. I used A for different things before, but now I'm using it for the adjacency matrix of my finite graph E. So we apply Perron-Frobenius theory to this matrix. We find Perron-Frobenius eigenvalue and Perron-Frobenius eigenvector corresponding to it. And then with these quantities at hand, we define the canonical trace on the AF subalgebra by this formula. Now, it is important in the calculations that the standard conditional expectation on the diagonal Massa preserves this Perron-Frobenius trace. However, there is one little catch which caused us quite a lot of problems. The shift endomorphism, which plays a role, because notice I use it for the construction of this unital sequence and so on. The shift in general does not respect the trace. Trace is not shift invariant in general on a graph algebra. Trace, of course, is shift invariant on the Kunz algebra, which simplifies the calculations quite a bit, but in general, not on a graph algebra, unless this condition holds that is given here. So even for some very simple matrices to write, if you take this adjacency matrix, then the corresponding Perron-Frobenius trace on the graph algebra will not be, the shift will not preserve that trace. And this is one of the reasons why this, you have to be a little careful, and you have to do some a bit ingenious estimations in order to carry out the argument. I mean, this is perhaps something that one could easily overlook. I mean, its calculations are much simpler for phi invariant traces, but this is not the case in general.
Okay. What's beta for this example?
Sorry, again?
What is beta for this example?
Oh, I don't remember. You have to calculate. You have to calculate. I don't remember.
But let me at least, if you don't mind, let me at least draw the graph, okay? I can do it, I think. And then you tell me if I'm right. So I would have two loops.
You have two vertices, first of all. Yeah?
Yes, two vertices. I would have two edges going like this, and
then
here
four
I would have
loops.
4 loops.
Exactly.
Right?
Yep.
So that's the graph. Okay.
Yep.
And that's its adjacency matrix.
Yeah, exactly.
And now here, when I look at this equation, it will be 3 and 5. Okay. So we know that beta is not 3 and 5 here.
Yep.
Okay.
Okay. So actually, this is the end of my talk, except for the literature. So I would like to put the 3 papers that are most directly related to what I talk about in historical order. So I partially actually discussed them already. The first paper due to Roberto, Jonki, and myself, here we dealt with the situation of how quasi-3 automorphisms of Kunz algebras, how they move, how they move diagonal massa to a massa which is not inner conjugate. In the second paper here by Tomohiro Hayashi, Jonki Hong, Sofia Mikkelsen, and myself, we proved that the theorem about quasi-3 automorphisms applied to graph algebras, but by, as I said, ad hoc method. However, I should say, in that second paper, we also considered the question of inner conjugacies of other algebras than Masas. In particular, we look at the question applied to the UHF subalgebra of a Kunz algebra. Yeah. And we found some conditions that allow us to conclude that if you move UHF subalgebra of ON by certain type of automorphisms, then the image is not inner conjugate to the original UHF subalgebra. It was again somewhat ad hoc method, but also involving some estimations and convergences using traces. So although different from this condition red star that I have here, but also looking at convergences in terms of trace norm of certain sequences of elements played a role there. So it has, in spirit at least, it has some similarity, that technique, to the one, although different, that I mentioned here. And finally,
well, wait again. What are your assumptions here on graphs in this paper?
As the same as I made here.
Okay, so it's finite.
The same. Yeah.
With an exit and what transitive? Yeah.
I mean, they were slight. Yeah. I mean. And finally, this is not a paper yet, the preprint available on the archive, joint work with Tomohiro Hayashi, Jong Hyong, and myself, in which we essentially, the main point here is what was the point of my talk, that is advertisement for that method that we believe could become quite general. I mean, it still needs some polishing, but we believe it has very good potential for providing a very useful tool for addressing that question that I asked at the beginning. Are two Masas in some purely infinite algebra, simpler algebra, are the inner conjugate or not? In particular, two Masas which we know that are possibly outer conjugate, which in turn could have implications on, give some insight into the structure of the outer automorphism group of such algebras. So anyway, so that's essentially all I wanted to say. In some sense, it's a work in progress, but I would want to.
So what do you mean by two here? It's like
promising results.
Second incarnation of the paper.
Well, if you look at the title of this second
okay,
paper,
it's the same.
It's very similar.
Okay.
So we added two, not to be accused of plagiarism by some, machines that are running through, archives and everything else. Yes, it's almost the same title as above here. Okay. So we added that too here. So. Thank you very much for your attention. This is the end of my talk. Thank you.
Mangatak. Okay. Great. So we have still plenty of time for questions. So let's grill Wojtek further on. Before I ask the audience to come up with questions, I have just a trivial question. I just want to do it fast before we forget. Wojtek, could you please go back a few slides, like 2 slides back?
Tell me
there was this
when
X. I would now forward for this XV. Where some of this XV, and I got confused.
For this Perron-Frobenius.
Yes. What is this XV?
Well, it's a coordinate because this adjacency matrix you can rows and columns indexed by vertices of the graph.
Yes.
So this is coordinate of x of v is the coordinate. This is a vector. It's coordinate corresponding v coordinate of that vector.
So
instead of giving coordinates, first coordinate, second, so coordinates depend on correspond to vertices.
Yeah, but here this vector, that's just a sequence of integers, right?
Adjacency matrix is a sequence of integer integer entries, but this is a vector simply. It has positive. It's a real number. Each coordinate is positive real number.
So
it doesn't have to be integer.
Okay. So if your adjacency matrix is say n by n, where n is the number of vertices.
Adjacency matrix has indeed non-negative integers as entries. That's correct. But this is a vector in the sense of a vector in Rn.
In Rn, that's what I want to say. This is in Rn, and basically you're saying that every entry of this vector is positive.
That's right.
Okay.
I mean, that's Perron-Frobenius theory. I'm not presenting it here. Okay. I mean, you have to prove something. I got
confused here, but now it makes perfect sense. All right, guys. So now it's your turn to grill Wojtek. So please fire at will. Tomek, show yourself. Yes.
I have a question. In the theory of compact semi-simple Lie groups,
yes,
there is a notion of a Weil group.
Yes.
Which is the normalizer of the maximal torus divided by this torus.
Excellent question.
So this is a very small group, very small invariant.
That's right.
Is, for instance, an analog for Masas of this?
It's an excellent question. I mean, I was waiting for this question because we are coming here to this point. So okay, this is very general, but let's think of this. Take this M to be ON, Kunz algebra ON. Okay. Then, if you can define this Weil group exactly as Tomasz said, for semi-simple Lie group in this case, for the diagonal. And what it turns out that it will be countable discrete group, okay? And actually, I'm not sure if Joachim Kunz used that term, but later in my papers with Roberto and with other people, we use this word. We call it the Weil group of the Kunz algebra, and more generally Weil group of a graph algebra, because this can be extended to graph algebras as well. So the difference is that in this case, this group is not very small, it is infinite. But however, it is discrete. It is countable discrete group. It is still very complicated, but I mentioned that quite a lot of progress has been made in that direction. And in particular, we have, well, I cannot say complete understanding, but we have quite some understanding of how it looks like. Maybe Roberto could comment on that, maybe Roberto doesn't agree with me, but quite a lot of work has been done in that direction. This concept does exist. Of course, as I said, it's an infinite group in this case, but it's accessible to large extent object. It's a very interesting object.
Oh, there is a lot of things that can be done regarding the understanding how this group is. Even looking for elements is a non-trivial task.
That's right. But I would say that we already learned quite a lot. I mean, it's not that it's completely, unknown object. Of course, there are lots of questions that are open, but we already know something about it. It's a very interesting object. It's a very interesting object from many respects, from combinatorial aspects, but also from the point of view of actions on the spectrum, of the diagonal. It's very interesting object. So I definitely would like to thank Tomasz for that question.
Okay, Tomek, are you satisfied?
Maybe I
My
answered
internet
not
crashed
in
for a
this
while,
sense.
so I haven't heard this answer, but I hope I could find it on YouTube.
Okay, so ask a question and when you switch yourself off. Okay, Jacek, go ahead. Hello, Glasgow.
Hello, thank you for the talk.
Yes.
So I wanted to ask about, in particular case of Kunz algebra, about automorphisms. So you mentioned a few classes of outer automorphisms that are more or less concretely described using action generators. The question is it the complete list of automorphism?
No, I didn't say. You are probably referring to this one.
Yes.
So notice these are certain examples, but first of all, you can multiply them and take various combinations of them in an obvious way. And then I also left room for these exotic ones.
Yes, but
notice in the case of Kunz algebra ON, everything is here. That's everything in the case of Kunz algebra ON. But for a general graph algebra, there are more.
Okay, yeah, so I wanted to ask concretely about the Kunz algebra. So in this case,
in the case of Kunz algebra, everyone is of that type. That's the original work of Kunz, that every endomorphism even, and in particular automorphism of ON, is of that type. In graph algebra, there are these others, but in Kunz algebras, that's all. However, I should point out that this is not so completely trivial, because it could be quite challenging and sometimes extremely difficult to determine for a given unitary whether lambda u is actually automorphism or a proper endomorphism. This is not trivial. This is not algorithmic. There's no algorithm that would tell you, if you give me in Kunz algebra, I'm talking Kunz algebra right now. If I take a unitary in Kunz algebra, there's no algorithm that arbitrary unitary, there's no algorithm that would tell me whether lambda u is an automorphism or a proper endomorphism.
Mm-hmm.
So yes, every automorphism is of that type, but it is still quite non-trivial. We don't know exactly which unitaries, correspond to automorphisms.
Yeah. Mm-hmm.
We have some classes, but not complete understanding. Far from that.
And just a silly question: if you would have identity between automorphisms, does it imply identity between unitaries that give these automorphisms?
Yes, I mean, yes, of course, yes.
Just to make sure.
Yeah.
Just to advertise while groups, we have a nice answer for recognizing automorphisms for the restricted, for the elements in the restricted while group. So.
Yeah, I mean, yes, exactly. So as I
very nice.
Yes, so in certain cases, like in certain cases of localized automorphisms here, there are algorithmic procedures that are highly non-trivial, but purely algorithmic. You can run an algorithm, not hopefully, but best on your computer, and that algorithm would actually tell you whether you are talking about automorphism or not. So this kind of work has been done, and there are some very fine results of the type. And we used quite a lot of computer time, right, Roberto, to analyze these things. So yes, that's a very good point to add here, that there are some interesting classes that we have actually algorithmic procedures for that.
So maybe follow-up question, if I may.
Yeah, go ahead.
Is there known some other maybe class of graphs algebras, which would in particular contain Kunz algebras, where this concrete outer automorphism generate whole outer automorphism group?
Oh, I must say that I cannot give an answer just on top of my head, because I haven't actually investigated that question myself. But okay, I don't want to give misleading. I don't have, on top of my head, I don't have clear answer to your question, so I don't want to give it. I mean, I'm trying to think. It may exist in the literature, but it's not right now in my head. Yeah, one could think about that.
Okay, thank you very much.
Sorry, but I cannot answer. Mm-hmm.
All right, anybody else? I don't see any raised hands.
I have. Oh,
okay.
Sorry.
Go ahead.
My second question is about some kind of space of Masas.
Some kind of what, sorry?
Space.
A space of Masas.
Space.
Do they have some structure?
Like principal ideal space, right?
Yeah.
Space of Masas.
Or primitive ideal space.
Yeah.
Well, but when you say space of Masas, are you thinking of some kind of topological space?
Topological space, yes.
You are thinking of topology.
And the structure of this space, especially how they are glued with orbits of Masas under inner automorphism, for instance.
I think that would be perfect if we had such a structure. I don't know of it. But
not even in simple examples?
But what do you mean by simple example?
For AF algebras?
This could be. For AF algebras, it could be. I don't know. I'm interested here in these purely infinite algebras, and for them, I don't think so. For AF algebras, that I think it's more likely. Yeah, it's definitely more likely. But for Kunz algebras or purely infinite graph algebras, I don't know. But this is an excellent question. I mean, if we could answer this, if we could have this kind of structure, that would be beautiful. Mm-hmm. Yeah, I mean, that would be beautiful. Yeah, I would love to have this kind of structure, or at least have some some idea how to cook it up. That would be very nice. But I don't have it for not at the level, not for Kunz algebras. But it's excellent question. Yes.
Mm-hmm. Okay. Anybody else? Adam?
Okay, so maybe related to this previous question, but typically how much suppose that I have some C-star algebras, and then I'm looking for Masas up to, in general, isomorphism, not necessarily an inner one. So typically, how many such isomorphism classes?
Well, when you say isomorphism, you mean outer conjugacy, or you mean isomorphism, algebraic?
Just abstract algebraic isomorphism.
I think in general, I'm not sure if it's actually known even how many of them, like for Kunz algebras. Maybe Roberto knows. Roberto, do you know if this question is known how many different types isomorphism classes in Kunz algebra? I don't think this is known actually, but many in general. You should expect many.
I agree that no, in general, I don't know.
There's no answer. There is no information of that type.
In general, I have quite different kind of masses.
They are exotic masses. They are masses that look very different from the standard diagonal. And I can only imagine that there is a great many of them. You know, when I say great many, that you cannot count them 1, 2, 3. I mean,
I'm asking this question since in the most basic example, but this is a von Neumann example, just take B of H, then correct me if I'm wrong, but as far as I know, there are only 2 Masas, which is L infinity sequential L infinity and L infinity continuous version.
This continuous, and but are you sure that these are the only 2? This I don't know. Of course, these are the 2 classical examples, but are you sure that these are the only ones?
I'm not 100 sure, but
I'm not a von Neumann algebra person, so I don't know.
As far as I know, there is a classification of commutative von Neumann algebras, which can be represented on a separable Hilbert space, and this classification is very explicit. It's like L infinity, L infinity right. Plus direct sum. For example, this continuous L infinity plus L infinity sequential, but
okay, von Neumann algebra situation is very special. Now notice that due to this whole machinery of these Poppas, and big schools, Valles, Ozawa, I mean, there are lots of cases known that you can count up to conjugacy, up to inner conjugacy Masas in some factors, and you can say exactly that there is only 1, or you can say that there are exactly 2 or 3, and things like that. But this is all in the context of factor von Neumann algebras. In the case, and I'm talking up to conjugacy, right, up to inner conjugacy. But say in the case of Kunz algebra ON, I cannot answer your question about algebraic isomorphism. But if you ask a weaker question, if you ask up to outer conjugacy, then uncountably many. Then then already from our work with Roberto, it follows that you have uncountably many classes. So you immediately go into huge numbers of different equivalence classes.
So Tom's suggestion of having a space is good.
Yeah. I mean, I like Tomar's suggestion. I mean, if you could elaborate a little bit how to put topology there. I mean, if we could prove, I mean, that could be very good step forward if this could be carried out, because we are not talking about 1, 2 objects. We are talking about some space, uncountable collection of objects. So if one could put reasonable topology there, then that could introduce some useful structure there. But I don't know how to do it.
If I could comment on that, there are some words relating, but not Masas, but all possible abelian subalgebras, and there are theorems of this kind that okay, this can be by inclusion naturally ordered, so you have a structure of partial ordering, and there are some theorems which states that if these partial orders are isomorphic, then in case of general C-star algebra, you can say that these are not star algebraic isomorphic, but only Jordan isomorphic, and up to commutative subalgebras. In the von Neumann case, these results are stronger.
I think that could be useful. I think this is also a very good comment. I mean, I have not investigated that, but it could be useful way to make some progress. I agree.
And the topology is the how it is called, Alexandrov topology, which is born out of this partial order.
Yeah,
it is a topology, but with pure axioms of separations.
Okay, so if I may comment on that, I mean, I think that your point is very well taken. However, if you would like to restrict this topology to Masas, then I don't think you will get anything interesting, because, you know, these Masas cannot be non-trivially contained one in another.
Yes, of course.
So for all abelian subalgebras, that could be a very useful object, but after restricting to Masas, I think you will get nothing interesting.
Yeah.
Yes, of course, but maybe you can allow for abstract embeddings, and then it is in general in this world of C-star algebra, it's not true that if you can embed one C-star algebra into other and the other one into the first one, then they are isomorphic. So you could maybe cook out some.
I mean, this is a good point. I mean, I think you are raising a very nice point. I agree. I cannot say anything because I have not worked in that direction, but I think this is a very interesting point that could be pursued further.
If I could comment, there is an approach in this vein of constructing so-called topos, consisting of all commutative subalgebras. Then Masas appear as a part of this construction, but it's not about restricting this theory to Masas, but presenting it's like presenting commutative subalgebras as intersections of Masas. So it's a slightly different direction. But for sure this structure is interesting, and at least for people working in category theory. It's about quantum logic, quantum theory of quantiles, and all this business. So this topos is important. Yeah.
Okay. Anybody else? I don't see any raised hands, so let me ask the final question, which is kind of obvious. Wojtek, would you elaborate, please, where you actually used your assumptions about your graph? I mean, finite I can easily understand, but
well, these are actually technical assumptions that things kind of make sense. You know, if you had some things or something, then you immediately run into special cases. Also, I mean, I want to have, for example, condition every cycle has an exit tells me that this standard diagonal is a massa, you know. So these are I don't use them in the proofs, but setup. If you exclude these assumptions, then you are already in a different setup. You know what I mean?
Yeah. But that's exactly what I want to hear. So if there is, if every loop has an exit, then you know that diagonals
this says exactly that, you know, that you are talking about massa. So
and what goes wrong with the sink?
And sinks, then it would cause some trouble for you know, when you construct Quasi-3 automorphisms or something, you would have some special cases. So we just wanted to, we made this assumption, not that we use them in the proof, rather, but so that there are some strange special cases that we would have to consider. So it's rather technical assumptions that everything fits into, you know, nice scheme of things. But you could, of course, consider some more general situations,
well,
but then you have to run into some special cases here and there. We just didn't want to bother with that, since for us the main point was talk about these pure infinite simple ones, and
you go beyond ON, and that's what matters.
Right? Yeah. We want to focus on the core of the problem, and not of some small technicalities that some, you know, something breaks down for some trivial reason.
So you explained exits, you explained sinks. How about transitivity?
Well, I mean, you could have, we don't want to have situations that the graph breaks down, you have, you know, some complicated ideal structure, then it's a different situation. We wanted to, essentially, we want to focus on simple, purely infinite case.
Okay.
We didn't want to go into ideal structure on that. That's the different story. You know what I mean?
Yeah.
So
yeah.
essentially, we wanted to look at simple, purely infinite unital case, and that's more or less what it is.
Okay, so
I mean,
if nobody objects,
graph,
Yeah,
that would be different story, but
yeah, because you mentioned that SUQ2 could be handled, but it's a different story. And
no, it's I mean, it's definitely different type of algebra. It's an extension of, you know, has ideal, and it's completely different type of algebra. So different type of problems you are addressing there. I mean, the type of algebra is completely different than ON.
Yeah, I've got you. No, that's you perfectly answered my question. So thank you so much. And if there are no objections, let's thank Wojtek again, Mangetak, for a wonderful.
Thank you very much for having me. And
I might say that this talk was fascinating, not only for masochists, so not only for people who work with Masas. I think that this talk was extremely enjoyable to everyone, and it was very, very nicely clear. And we really appreciate it very much. And with this compliment, let me stop recording.